Ta-da. Good morning. Happy Tuesday. I finished marking your tests. It feels like a long time ago. I didn't send out an announcement because it didn't feel very urgent, but you can find feedback. So what I did was I downloaded your work and then I wrote on the PDF and then I uploaded it again. And so you can find feedback from test number 2. It should be with your submitted work. With your submitted work. Now I'm going to show you where I put it, and hopefully, so if I go to our Moodle page in your test 2 work, actually, I don't want to do that because then I'll show someone's work and that feels, I can't remember who's at the top of the list, it doesn't matter. But anyway, so if you go into that file, I've uploaded a feedback file. So, and then you'll see my writing on there. And I chose pink for fun, but because red looks so glaring. So have a look at that feedback and that will tell you how I adjusted your grades. So the grades I have updated on Moodle, and so all your grades are up to date. So your total test 2 grade is on Moodle. So I looked at, what answers did you give me in WebAssign? Does your work match what you told me on WebAssign? Or maybe you made a little typo in WebAssign, so then I increased your mark a little bit and just kind of made it more realistic. So that's good. I can cross that off my list of things to talk to you guys about. Next thing I wanted to talk about is I managed to forget. I feel like that's all I'm saying this term. I know it's not, but it feels like I forgot. I have to do evaluations. So some terms, and you might have done them for other teachers already, but I would really appreciate it if you would do my evaluation. And it's available until Thursday, so Friday. I'll show you where to find it. And then let's see here. You go to Moodle, and then there should be a course added to your page. Might be a little bit later, but it should be a current course, and it's called Formative Evaluation of College Professor. So if you go there, and I don't know how it's going to work for me. Read the instructions. And here's the survey link. Okay, good. So then if you go to the survey link, okay, I don't think it's going to take you 25 minutes. Don't worry. But so there's usually 2 parts. I don't know if I can tell. Okay, so here. Okay, please select your professor. You're going to pick me, Lee. and then your course here. And then, so the part that that is most important is these, the survey portion. So the strongly agree to strongly disagree portion. And then I think there's going to be parts where you can kind of write your, man, they don't hold back. Oh yeah, these comments are just going to go to me. So if you're having a hard time, I always used to have a hard time coming up with stuff to write in these comments. And I always felt like I had to do it, but you don't have to do it. The strongly agree to strongly disagree portion, that's the important part. That's the part that goes to my boss, and they need to kind of keep an eye on how things are going. So those values go to my boss, and then which is the dean, and then the comments just go to me. So if you're running out of time or anything like that, then don't worry about the comments. What is important is the survey part, if that makes sense. Okay, so like I said, just to recap here, you should, in your Moodle dashboard, in your courses in progress, you might have to kind of search around here, but you should have a formative evaluation of college professor. Oh, Wendy's already done it. Nice. I know it's because I got the reminder email and I was like, uh-oh, I need to tell my students about this, not just, oh, okay. I'm not used to them being online. It's nice. We used to have packages and bring them around. Constant reminder. So I would really appreciate it if you could do my evaluation. I would really appreciate if you would do my evaluation. I'll even put in anyways. Okay. I used to be more on the ball because that's how you get work, but now I'm full-time, so now I'm a little bit lazy. But it'd be really great if you could do that. Great, cross that off my list. Okay, so today we're gonna start trigonometry. You might remember trigonometry, things like SOHCAHTOA, kind of maybe ringing a bell at some point. So we'll review all that stuff. But today we're just going to lay some groundwork. So here's the thing with trigonometry and how we approach trigonometry. There are kind of two ways that you can do trig. Let's call it trig. Not two ways, but there are two approaches that you could use. And I'm going to introduce them both at the same time. So it's going to feel like, oh, but we just did this. What's the difference? There is none. Okay. So we're going to do 5.1 and 6.1 kind of side by side. And I want to make those connections because it's really just introducing two ways that you could approach these problems. And then the reason we do that is because it depends on what the problem is. Sometimes one of the methods kind of lends itself better than another method. But for us, it doesn't really matter. If you pick a method that you like, then that's great. And I'm going to try to keep just kind of using the same method just because I find that trig can be really confusing sometimes. So today we start trigonometry. trigonometry, which is on chapters 5 and 6. I'm going to say it right now, we're not going to make it to chapter 7. Chapter 7 is just kind of like more trig, so we're not really missing out. As long as we can do these sections in chapters 5 and 6, we're good. So trigonometry is quite different from what we've been doing, right? And so I'm gonna try to go nice and slow, but also try to cover some ground. So here we go. We will cover, and you know what? I need to, I was hoping I had like a little grip for my, I write way too hard and it just, towards the end of the term, it just hurts my hand. It's crazy. So we will cover, so I'm gonna try to write lighter. I don't know. We will cover 5.1 and 6.1 at the same time. At the same time as they introduce the same concepts, right, but just in different ways, as they introduce the same concepts in different ways. And then we're going to do the same thing with 5.2 and 6.2. And then from there, I'm going to pick and choose. Okay, we're going to do the chapter 5 method, the chapter 6 method. Sometimes you won't even know the difference, but just I go with it. Okay, so I realized, so last term my iPad broke. So this is a new iPad. And actually it was the pencil that didn't work, but anyways, doesn't matter. So I realized I don't have notes for trig, but I realized it kind of too late. So I've posted the notes that I do have, and then I'll work on kind of finishing those up with the solutions, because I realized I didn't have the solutions. That was the problem. But I'll post those soon. So 5.1 is talking about the unit circle. So, so one approach that we could use is the unit circle approach. And we'll kind of look at, and that's the one that I'm going to rely on a lot. And so let's talk about the unit circle first off here. Okay. So the unit circle is just a circle with a radius of 1, and it's centered at the origin of the xy plane. And I actually realized, I have a typo. Oops, I have a typo in, and the worst part is, I wrote it. Recall quadrants in a circle. I don't know why I said in a circle. I think it's because we're talking about the unit circle. But it should say in the xy plane. In the xy plane. Okay. So I'm going to just kind of remake this, or actually, let's bring this all in here. Copy. Okay. So the unit circle is the special circle that's centered here at 0, 0, so the origin, and it's got a radius of 1. Okay, so the unit circle has a radius of 1, and recall that any circle with radius r has formula, not really formula, I guess. Yeah, it is. X squared plus y squared equals r squared, right? But if the radius is 1, so that's why the unit circle has x squared plus y squared equals 1. Therefore, the unit circle with r equals 1 is x squared plus y squared equals 1 squared, which is just 1. Okay. So let's see here. So we've got the equation of this unit circle, and what we're going to do is we're going to talk about points around, I kind of went off track there, points around the unit circle. So we're going to talk about just kind of the circumference. And if we're talking about the circumference, right, of a circle, then the circumference is 2 pi r, right? And so we will talk about points around the circumference which in general, the circumference is 2 pi r, right? But the circumference for the unit circle, 2 pi 1, right? The radius is 1. That's the definition of the unit circle. And so here, the total distance, remember the circumference is the distance around the circle. So the distance around a full loop, let's call it, is 2 pi, right? So therefore, the distance around the unit circle is 2 pi. Okay. So that means that we've gone from any starting point, we've gone around one loop, we've gone a distance of 2 pi. And so it's a little bit tricky because for now, we're just going to talk about the distances around this circle, and then it's not until chapter 6 that we say, oh, well, actually, these distances around the circle are also going to be the angles, okay? We know trigonometry has to do with angles, and so where are the angles? But the angles are going to be the same as the distance around the circle, and I know that is kind of hard to wrap your head around, okay? So what we will find in 6.1 is that the distance around the circle is that the distance around the circle, I guess I should say that it works for any circle, but I'll say the unit circle is equivalent to the angle, okay? Is equivalent to the angle. Okay. So for now, let's just kind of keep that in the back of our minds, and then when we finish off with 6.1, we can make that connection. But I want you to kind of see that before so that it's not so weird. Okay, so what happens if we just go back to our quadrants, right? We're going to need to talk about our quadrants. So here's our quadrant 1. So we start in the positive quadrant, right? And by that I mean x is positive and y is positive, right? In quadrant 1. Here in quadrant 2, x is negative, y is positive. Quadrant 3, x is negative and y is negative. And in quadrant 4, x is positive and y is negative, right? And so talking about these quadrants, and here I've got quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Here x is positive and y is positive, right? In quadrant 2, let's just outline what we said earlier. X is negative and y is positive. Okay. In Q3, x is negative and y is negative. And in Q4, x is positive and y is negative. Okay. The reason we need to keep track of these quadrants and when is x positive or negative is because what that allows us to do is, if we can just memorize how things behave in quadrant 1 when both x and y are positive, if we're trying to look at distances around the circle, right, then we're going to end up at xy coordinates, right? And so if we know how quadrant 1 behaves, then we can say, oh, okay, by symmetry, in quadrant 2, it's going to be the same, except now x is negative and y is still positive, for example. Okay. So by symmetry, if we memorize Q1, if we memorize some key points on the unit circle in quadrant 1, we can use those to find points in the other 3 quadrants. We can use those to find points in the other 3 quadrants. Okay. So we're going to talk about the distance around the circle, but the distance around a circle is equivalent to an xy coordinate. Okay. So we want to talk about the distance around the circle, which we later, right? Later we call this the angle. Later called the angle. Okay. So we want to talk about the distance around the circle, which will put us at xy coordinates. Which will put us at xy coordinates. Okay. So let's start with just some little examples here. So let's just confirm that some points are on the unit circle. Oops. Show that the point is on the unit circle. And so let's do, oh, it looks like the root was cut off. That seems weird. Sorry about that, guys. Let's do number 7. How do we show that something's on the unit circle? Well, if it's on the unit circle, then we know that where it's way up here at the top, that x squared plus y squared equals 1, right, to be on the unit circle. So here, need to show that x squared plus y squared equals 1. And remember, ordered pairs, right? These are all ordered pairs. These are all just one point in the xy plane, and it's x comma y. So for 7, we have an xy point of negative root 5 over 3 and 2 over 3. Okay. So what I want to do is I want to take that x and that y. So here, this is my x, and this is my y. If I square each of those and add them up, it has to add to 1, right? Otherwise, it's not on the unit circle. So I have x squared plus y squared. Does it equal 1? Because we want to see if it is on the unit circle. Wait, whoops. Sorry, I'll slip. Here they're saying show that the point is on the unit circle, so we will find that it is. But doesn't matter. We're just confirming in this case, but sometimes the question will ask, is this point on the unit circle? And then you definitely need this little question mark here. So I've got my x squared, and then my y squared is 2 over 3 squared. Does it equal 1? Now, remember exponent laws? Ugh, long time ago, right? Well, they've been haunting us ever since, but if I'm dividing inside here, I can bring the square inside, and so I get, let's see here. I can do negative root 5 squared over 3 squared plus 2 squared over 3 squared. Does it equal 1? Oh, that doesn't look like a square. 3 squared is 9, right? So I still have that common denominator. That's nice. So then I have the negative root 5 squared. Now, this is technically negative 1 times the root of 5, right? So you could put the square on each of these, or you can just say, well, when I square something, it becomes positive. And if I square a square root, I just get whatever's inside, right? So this becomes 5 plus 2 squared is 4 over 9. Does it equal 1? 5 plus 4 is 9 over 9, which equals 1. Therefore, the point is on the unit circle. Therefore, the point is on the unit circle. So that's how we can confirm that points are on the unit circle. We are going to focus on 3 points because I don't count the axis points. But we're going to focus on 3 points that are going to be kind of critical to solving all these problems. On the one hand, it's going to feel like a lot in the beginning, but then if you just kind of step back and say, well, I only need to remember 3 points, then it's a little bit better. Okay, so there will be 3 points. There will be 3 kind of special points. 3 special points that we should memorize. And when I say memorize, I mean have it on a cheat sheet somewhere, because of course all our final exam is open book. So, but you do want to have it kind of handy, and just kind of know that if we were in person, you would have to memorize it. But you guys are lucky in that sense. So there will be 3 special points that we should memorize on the unit circle in quadrant 1, which we already talked about, right? If we know what the points are in quadrant 1, then we can replicate them in quadrant 2, 3, 4. Okay, so those points, I'm just going to go for it here, are on this handout. Let's just talk about these. The points, the XY coordinates are in the brackets, right? So those are the actual points. These are the distances to those points. Notice that we're talking about pi over 6, pi over 4, pi over 3. That looks terrible, but when we introduce radians, it's all going to make sense. Remember that we said the distance, the total distance around the whole circle is 2 pi, right? So that's why we're going to be working in kind of increments of pi. So pi over 6, so these are the distances. Let's see if I can kind of highlight that. Distances. Let's see once I zoom out. And then these are the actual XY points. Okay. So if we just kind of, there. Let's zoom in on just quadrant 1. Quadrant 1 looks like this. Okay. If we said that the whole distance is 2 pi, right? So the whole distance around the circle is 2 pi, then half the distance must be pi, and then a quarter of the distance must be pi over 2, right? And so that's how we end up here at pi over 2 is this distance to this point. Notice that I'm starting here on the positive x-axis. We're going to call that standard position. So when we measure distances, we usually start at the on the positive x-axis. So when we measure distances around the unit circle, we start on the positive x-axis. If we think about this, right? Okay, so I'm saying I'm on the x-axis here. What xy point would this be? If it has a radius of 1, right? I've got a radius of 1, so I'm out at x equals 1 and y equals 0. So this point is at 1, 0. Okay. So we start on the positive x-axis, and we call this, and we will later call this, standard position. Okay. So all our distances around the circle, which later we're going to call angles, right? They start here at 1, 0, because we've got a radius of 1. So we start on the positive x-axis, and then we're going around this way. Okay. So the quarter wave marks are all a distance of pi over 2. So pi over 2, pi, 3 pi over 2, 4 pi over 2 reduces to 2 pi, right? So another key cutoff point is the quarter wave mark. Okay, so the quarter wave mark, let's put it kind of here, is halfway to pi over 2. So let's call this pi over 4, right? Pi over 2 is pi over 4. Okay. So that's going to be another important point to keep track of. Now, if I go pi over 4 distances around the circle, right? I would go pi over 4, and then another distance of pi over 4 puts me at 2 pi over 4, which reduces to pi over 2, right? And then I can go another quarter wave mark, 3 pi over 4, 4 pi over 4 reduces to pi. Okay, so it all checks out. And then 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, we're back to 2 pi, right? And so this pi over 4 check-in point is going to be really important. Okay. Pi over 4 happens to be at a point, and this is going to be weird. We can confirm that it's on the unit circle, but pi over 4 is at the point and this is where the memorization comes in. Pi over 2, root 2 over 2, root 2 over 2. Oops. Okay. Sometimes we might say 1 over root 2 instead of root 2 over 2, but all I've done is rationalize the denominator, right? So, so this point is going to be important. Now, root 2 over 2, root 2 over 2, how I remember it is, okay, if I'm at some quarter wave mark, then the x and the y values are the same, right? If I move into the second quadrant, right, now by symmetry, I'm still at root 2 over 2 and root 2 over 2, except now my x has to be negative. So that puts me at negative root 2 over 2, root 2 over 2. Okay. So let's just kind of map this distance in orange. And I should map this distance in pink. There, kind of trying to be careful here. We can talk about the point that pi over 2 is at as well, right? But it's going to be a lot easier than root 2 over 2, root 2 over 2. Where did that come from? Don't worry. You can find it, but more for us, we can confirm that it is on the unit circle, and then just kind of take it as a fact. Okay, root 2 over 2, root 2 over 2. That's if I've moved a distance of pi over 4. Okay, pi over 2, now I'm on the y-axis, so with a radius of 1, putting me at x equals 0, y equals 1, right? And so here, at the point x equals 0, y is 1. Okay, and I think we've already established that this is at 1, 0. Okay, so we can split it into quarters, so the whole circle into quarters, or we can split them into, I guess, eighths. But if we think about this, just the first quadrant, we can split them into pi over 4, right? That's the halfway mark. The next important distance is going to be pi over 3. So now we're cutting each quadrant or each, I guess, half circle into 3. So let's draw it again. So another important cutoff point or another important distance is pi over 3. And pi over 6. Maybe I should say pi over 6 instead. Pi over 6, if the distance of the half circle, okay. Now let's focus on, right? This distance was a distance of pi. Pi puts me at negative 1, 0. Right. So now if I cut this into pi over 6, okay, what I end up at is I get pi over 6, right? I'm slicing this thing into 6 parts, right? Because this is a distance of pi. So pi over 6 is this thing divided into 6 parts. So what happens is I get pi over 6. Let's do 2 pi over 6. 2 pi over 6 is the same as what? Pi over 3, right? Uh, 3 pi over 6, and maybe I should bump this down just a little bit. There. 3 pi over 6 is the same as pi over 2. 4 pi over 6. Do we simplify that? I think 4 pi over 6 is going to be, I just can't remember if we keep it as pi over 6 or pi over 3. No, I think we write it as 2 pi over 3. And then 5 pi over 6, which that one we just leave. Okay. And then 6 pi over 6, which is just pi. Okay. So from this pi over 6 distance, we can also talk about pi over 3, right? And so pi over 6 and pi over 3, we're going to treat them as kind of two separate entities. And so here, the points that we're interested in are at pi over 6 and pi over 3. I'm just going to map out in the middle here would be pi over 4. Right, halfway mark, so a third of the way, halfway, and then 2/3 of the way, and then the full quarter. So where are these points, right? So notice that by symmetry, this point from pi over 6 is going to map to having the negative version of x and the same version of y at 5 pi over 6. Right, so notice that this point, this point here is going to map to this point here, right, by symmetry. So that's what I mean by symmetry. If you just know what the xy value is at pi over 6 in quadrant 1, then if you're at 5 pi over 6, at an angle of 5 pi over 6 later, you know what the xy values are from just knowing what pi over 6 is. So that's why we only need to memorize quadrant 1. So, and this is at, so pi over 6, again, a case of memorizing here, is at √3 over 2 and 1/2. And then pi over 3 is kind of the switcheroo of that, is at 1/2 √3 over 2. So if we know what the point is in quadrant 1, then we can use it to map, we can use symmetry to map to all around the circle. Now, on Moodle, at the very top of the page, I've posted 2 trig formula sheets. So I'm going to go there, and we haven't used them yet, obviously, because we haven't done any trig, but let's see if I can get back to our course here. Okay. So at the very top, I've posted, or it's been there, but the Math 120 formula sheet, it says optional. You don't need to use it if you don't want to. If you don't like it, then that's okay. And then there's also a trigonometry formula sheet, which I find really, really useful. So let's go to the trigonometry formula sheet. I'm just going to bring it into my notes here. Oh, done. Okay. So from this formula sheet, it looks bad, right? But we do have the unit circle here, and that's what I'm here for. So I'm just going to grab this. From the trigonometry formula sheet posted on Moodle, we have this. We have the unit circle. Okay, so what it's done is it has gone through and just plotted out all the points, right? Pi over 6, 2 pi over 6 reduces to pi over 3, 3 pi over 6 reduces to pi over 2, 4 pi over 6, 2 pi over 3, 5 pi over 6 stays 5 pi over 6. That's what I was kind of juggling around. if we reduced it, and we do, to 2 pi over 3. 5 pi over 6, 6 pi over 6, 7 pi over 6, right? And so we've got these kind of pi over 6 increments here, 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 right? Cutting each of these into little sixth of the half, right? Pi is the half distance here, or the full distance is 2 pi, right? So 12. Okay, so those are most of the cutoff points are at the pi over 6 marks, but remember, if you can reduce it to something over 3, right? 2 pi over 6 reduces to pi over 3, then you can switch the xy coordinates. So root 3 over 2 and 1/2 becomes 1/2 root 3 over 2. We've also got the quarter-way marks, which is pi over 4, also 2 pi over 4, which reduces to pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4 puts me at 2 pi. Okay, so you can either work on just memorizing the first quadrant, or you can just have this unit circle that I've given you. But notice, right, then notice that the x value here is root 3 over 2, and in quadrant 2, remember, that's why we went through and talked about, okay, here x and y are all positive, which is reflected by all of these values being positive. In quadrant 2, all my x values are negative, right? But all my y values are positive. Right? And you can just kind of go through and sort out all these points, and what you'll find is that there are really only 3 points that you need to memorize. And then in quadrant 3, right, both x and y are negative, which is reflected here in them all being negative. So here, let's just kind of talk about these guys. Q1, x is negative, y is positive. I should use a different color here. This one maybe. Q2. Q3, x is negative and y is negative. And then finally, let's see, I've kind of used up all my colors here, maybe purple. Q4, x is positive and y is negative, right? Which is reflected here. All my x values are positive, but then my y values are negative. So you can kind of go through, do the run through, and map all these points, but here they are just kind of listed explicitly, so that's nice. So I'm going to refer to this circle quite a bit because it cuts down on a lot of work, and if I give you 7 pi over 6, then you can just find 7 pi over 6 on here. And we're not going to have to deal with any other distances or angles, right? Later we'll call these angles the distances. But for now, we'll just call them distances. We're only going to deal with increments of pi over 6, pi over 4, or pi over 3, or pi over 2. So these are the only ones that we need to concern ourselves with. Okay, so good. Let's see here. What I want to do is let's just talk about some terminal points. So what's going to happen is we're either moving clockwise or counterclockwise. And just as a convention, the distances that are positive are actually moving counterclockwise, right? As we've noticed, right? Because we start here in standard position and then we move up and around the circle this way. And so positive distances around the unit circle positive distances around the unit circle are moving counterclockwise. Okay. While negative distances, so if I tell you a negative distance of pi over 6, what that means is that you're moving clockwise a distance of pi over 6, which would put you at the same point as 11 pi over 6 if it was positive, right? Notice that we can get to the same point moving clockwise or counterclockwise, right? So while negative distances are moving clockwise. Okay. So got this little visual. Okay. So here, the distances, we're denoting distances by t, a lowercase t. So if t is the distance, around the unit circle, then we end up at what we call a terminal point, right? So terminal means the end. And so if we move a distance of t, we end up at pxy, which is the terminal point. Now, if we've got a negative distance, then we move clockwise around the circle. But again, we're just going to end up at a terminal point. Now, trig is hard and that's okay, but let's have a little break. Let's have a break until 9:06. And then we'll keep going. We'll talk more about terminal points after this. Break until 9:06. How about that? We're back. Delete. Okay, so what I want to do is let's just talk a little bit more about those terminal points. We know that each distance is of course associated with a point, but now we're gonna work on our skills on figuring out what those points are if I give you a distance. So let's see here. Let's grab. We'll just do 1 or 2. So I want to find the terminal point, which is that xy coordinate, right? On the unit circle, so that's good because we know how the unit circle behaves, determined by the given value of t. Now t, remember, is what we're going to use to denote the distances. But also, let's just keep in mind that t is later going to be an angle, and often an angle is denoted by a theta, a Greek letter theta. We'll hold off on that for a little bit, but that's why t and theta are the same. So t is the distance around the circle. Okay, great. We know that the full distance around the circle is 2 pi, and so we're going to use that to figure out where each of these points end up. Okay. So 24, if I think about my xy plane here, let's just draw a quick circle here. If I move a distance of 4 pi, well, I know that from here, right, if I go around once, that's a distance of 2 pi. If I go around another time, whoops, that's another 2 pi. So that puts me, right, if you think about it, it puts you back at the same point where you started. And because we're starting, we're always going to start on the xy or positive x-axis here, so at 1, 0. Then the terminal point, pxy, is at 1, 0, right? Because I've just gone 2 loops around the whole circle. Okay. So good. Hopefully that one was okay. Right. Let's go to 24. Oh, I said 24, but this is actually 23. That would have been confusing, wouldn't it? Okay. Now I'm moving a negative distance, right? So now I'm going clockwise 3 pi. Remember, 2 pi puts me back at where I started, and then I keep going clockwise for another distance of pi. Right, so negative 3 pi. The negative means I'm going clockwise, and 3 pi is really the just clockwise 2 pi plus pi, right? If we want to kind of break it down that way. So we want to kind of extract the full loops around because they don't actually do anything, right? We end up at the same terminal point. Since a full 2 pi gets us back to the same starting point. So what we're interested in is that extra pi. Where does that put us? Especially, or in this case, negative pi. So here, we can kind of ignore the negative 2 pi. Negative 2 pi, because it puts us back to here where we started at 1, 0. Now I want to go another distance of pi, and just knowing that a distance of pi is halfway through the circle puts me here. So pxy is when x is -1 and y is 0, right? Because I know this is my, this is the origin. I've got a radius of 1, right? And so -1, 0. You could also have used the unit circle that we just introduced here and said, okay, well, -3 pi is -2 pi, back to here, and then negative pi puts me here at -1, 0, and that is the terminal point. Okay. So far we've ended up on the x or well, just the x-axis actually, not the y-axis. Could have. But so far our terminal points have been kind of nice to look at. Let's do, I guess all of these are going to be kind of nice, but let's just do 25 and then I'll leave you to do 26. 3 pi over 2. It's positive, so I know I'm moving counterclockwise, and 3 pi over 2 remember, pi over 2 is at the quarter way mark, right? Because pi is the halfway mark. So pi over 2, 2 pi over 2, 3 pi over 2. Okay. So from here, right, I can go a distance of pi over 2, oops, and then 2 pi over 2, which is just pi, right? 2 pi over 2 reduces to pi. And then 3 pi over 2 is at the point. Now, knowing that we're working on a circle with a radius of 1, and on the y-axis, x is 0, and I'm on the negative y-axis, so I'm at 0, negative 1. Which, again, you could have just grabbed from this unit circle, right? Especially because 3 pi over 2 is on here. Okay. And the terminal point is at 0, negative 1. Okay. So these are all the terminal points. And maybe I'll highlight this here. Terminal point. We also have on the handout, you've got a table. It depends on if you like the circle visualization or if you just want to flat out memorize these things. Then you've got this table. I actually like the circle visualization, so I'm not gonna bring in the table, but it is here in case you want it. Okay. But again, it's just the points that we were talking about earlier, these terminal points, right? So these are terminal points because it's where we end up if we go each of these distances. So let's see here. From in the next section, we introduce coterminal, but I think this is a nice place to introduce it, right? So two distances or angles, because they're going to be the same. Two distances, right, which are later going to be angles. Two distances that end up at the same terminal point are called coterminal, which makes sense, right? So two distances that end up at the same terminal point are called coterminal. Okay. If we think about maybe, where's one? Okay. If I draw my unit circle again, Well, it's a bad circle, isn't it? I'll try again. I'll even let technology do its thing. There we go. So here, if I've got this circle, right, a distance of, let's grab from here, a distance of 11 pi over 6 in the positive direction is the same distance, right, as positive pi over 6, but in the negative direction, right? And so 11 pi over 6 and negative pi over 6 are what we call coterminal. So 11 pi over 6, oops, that should be 11. That's moving from here to there is coterminal, and maybe I'll do it in orange to show. So 11 pi over 6 is coterminal with negative pi over 6. Okay. So 11 pi over 6 and negative pi over 6 have the same terminal point, which is what? I want to say root 3 over 2 and negative 1/2. I'm going to confirm that, but what did I do there? I know that for positive pi over 6, it's root 3 over 2 1/2. So now I know that by symmetry, right, I know I can go down into the fourth quadrant and say, okay, well, x is still positive, but my y, I have to make it negative. So, but I'm just going to confirm that this is the terminal point on that unit circle that I gave you. Okay. I'll catch up here. Root 3 over 2, negative 1/2. Good. So they have that same terminal point, and in fact, that terminal point is this point. So good. Okay. So what we've seen here is that sometimes, right? Sometimes we can simplify things. Instead of talking about 11 pi over 6, what if we just talk about the closest distance from the x-axis? And that's what we call the reference point. Okay. So sometimes we can simplify distances by finding the how can I say the reference point without saying the reference number, I guess, or the reference angle. So sometimes we can simplify distances by finding the shortest distance from the x-axis to the same terminal point. Okay. And this is what we call the reference number. This is called the reference number. So the reference number, let's bring it in here. It talks about the distance from the x-axis. So if t is just any distance, right, then the reference number, we denote it by t bar, is the shortest distance along the unit circle between the terminal point determined by t and the x-axis, right? And so it just depends on where you are in your unit circle. And then the reference number is going to be referring to the distance, the shortest distance from the x-axis. So I've got a couple of examples here because it depends on what quadrant you're in. Okay. So depending on what quadrant you're in, of course, in quadrant 1, the shortest distance from the x-axis is going to be just whatever the distance is. So then the reference number is itself. In quadrant 2, right, instead of measuring this distance, we say, well, I could just as well end up there from the x-axis going up here, right? And so sometimes that's easier. I personally don't end up using reference numbers that often because sometimes I find them a little bit confusing, especially because we have that unit circle, which is a little bit easier to look at. So I will gloss over reference numbers a little bit here, but it's good to remember that they are coterminal, right? So they end up at the same terminal point. But notice that here, this reference number isn't measuring from the positive x-axis, it's measuring from the negative x-axis. So then we need to keep track of, okay, are my x's positive or negative, or are my y's positive or negative? So it gets a little bit messy. I will definitely use it for the fourth quadrant because just like we saw earlier, it will be easier to just kind of say, well, 11 pi over 6 is the same as negative pi over 6, and I know what pi over 6 is. So the first and the fourth quadrant I find are the easiest to deal with, and then when we're dealing with the second and the third quadrant, it becomes a little bit sticky, but we'll work on it. So what I want to do is I want to talk about how do we find terminal points, right? And next day, so on Thursday, we will be talking about, so the x-coordinate and the y-coordinate of the terminal point are actually going to be the cosine and the sine of these angles. So that's how we're going to get to this trigonometry. But we're going to parking lot that till Thursday. But so we need to talk about these points. How do we find these xy coordinates? Because later that's going to be our sine and cosine of these angles. So how do we find the terminal points for large values of t? So for large distances, in here, we're basically going to do the exact same thing that we were doing earlier. So if we want to find the terminal point for 29 pi over 6, what we need to do is we need to tease out full rotations of 2 pi, right? And so what we end up doing is you can do 29 over 6 and do 29 over 6 on your calculator, right? And you'll find that it's 4.833. So that's how they decided to pull out the full 4 pi, right? 4 pi is 2 revolutions and then some. So then we need to think about, okay, well, if I'm able to extract 4 pi from a fraction over 6, well, 4 times 6 is what, 24? 29 minus 24 pi over 6 leaves 5 pi over 6. Okay, so here. You know what? Let's just do our own. Actually, keep changing my mind. Let's talk about this one because I just used it. So here, 29 pi over 6 is the same thing as, so 4 times 6 pi over 6 plus 5 pi over 6, right? And that's how the 6 over 6 cancels. And so 5 pi over 6 is going to be coterminal because this is 2 full rotations. 4 pi equals 2 full rotations. So then 29 pi over 6 is going to be coterminal with 5 pi over 6. 5 pi over 6 is reduced as much as we can, but also we can grab 5 pi over 6 from that unit circle that I gave you. So therefore 29 pi over 6 and 5 pi over 6 are coterminal. And then if I grab that, like I said, I'm going to be grabbing this unit circle a lot. So from here, it means that, well, 5 pi over 6 is where it looks like I found 5 pi. I know, it's the dangers of trigonometry. Pi, pi, pi. Key lime pie, lemon meringue pie, raspberry pie, rhubarb pie. I know. Danger. So here, 5 pi over 6 is on here. And what you could have done is you could have said, okay, well, a full revolution is going to be 12 pi over 6, right? Because it's 2 pi, so when it's over 6, just knowing how fractions work, right? A full revolution would put me at 12 pi over 6, and then another 12 would put me at 24 pi over 6. And then what you could do is you could just go in increments of pi over 6. So 24 pi over 6, 25, 26, 27, 28, 29 pi over 6. Right, so regardless of how you get there, remembering how the pi over 6 or the over 6 increments work, right? The pi over 6 increments are here, here. Don't forget the quarter way mark here and here. So regardless, the terminal point that we need is this negative root 3 over 2 and 1/2, which we have here, negative root 3 over 2, 1/2. So the terminal point is terminal point. If we talked about the reference number, right? The reference number, well, I've gone 5 pi over 6, or this is a distance of pi over 6 from the x-axis, from the negative x-axis, right? So if you talked about the reference number, it would be pi over 6, and that's why we can map it across here. So that's how we can get the XY coordinates. But reference numbers, we only really need them if we don't have the full circle available, right? If we've only measured or memorized the first quadrant, then reference numbers are more useful. But for us, we have them all, we can see them all. So keep this circle handy. Okay. Let's do another example. Okay, I want to do, let's do, let's do 50. So we're going a distance of 17 pi over 4. And we want to find the reference number for each of these values and the terminal point. I'm going to focus on the terminal point. So here I want to focus on the terminal point. So what can we do? Well, I would say the easiest thing you can do is to, again, use this, the unit circle, right? Making sure, okay, so because I'm moving at over 4 increments, right? So now I'm working in kind of increments of quarters, working in quarter increments. So what can I do? Well, 17, I could go 17 quarters, tick, 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 tick. Or if I wanted to, I wonder if I can copy. Clean this up, make it fresh. Okay, so quarter increments are where? Quarter increments are here, 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 here. Right. These are all my quarter increments. Quarter increments. So you could, there's nothing really wrong with saying, okay, I'm just going to go 17 quarter increments. Here we go. 1, 2, 3, 4, 5, 6, 7, 8. Okay, no surprise there. 8 pi over 4 is 2 pi. Okay, so now I've got 8. If I do another 8, I'm at 16, right? So then another, to get from 16 to 17, I just need to go 1 quarter. And so here, where I end up at is just pi over 4, right? Which means that 17 pi over 4 and pi over 4 are coterminal, meaning they have the same terminal point. Okay. So moving around the unit circle, we find that 17 pi over 4 is coterminal with pi over 4 at a terminal point of root 2 over 2, root 2 over 2. Notice that all the quarter way marks, right, or at least the non-axes ones, are all root 2 over 2, root 2 over 2, right? So that's nice. You can kind of easily memorize that. Root 2 over 2, root 2 over 2. Okay. Alternatively, what you could have done is you could have broken up 17 into quarters to see how many quarters you have. So alternatively, 17 pi over 4 is the same thing, and what you do is just do 17 over 4 on your calculator. Oops. And you get 4.25. So it means I would move 4 pi and a quarter, which makes sense, right? That's what we found. And 2 of those 2 pi, this is going to be the same as 4.25 pi, just ignoring that pi, right? Where 2 revolutions, where 2 revolutions, or sorry, where 2 is 1 revolution. So 4 is 2 full revolutions. So what you do is you can rewrite this as 17 pi over 4 is 4 as a fraction over 4, right? And let's just take it nice and slow. 4 plus a quarter, 1 over 4 pi. But to get a common denominator, I need to multiply this by 4 over 4, right? Because I moved from a common denominator of 4, so I need to have 4 over 4 over here. And so I get 16 over 4, which is 4, right? So 16 plus 1 over 4 times pi, right? And so this is just 2 full revolutions. You kind of discard those because you're just moving around and around and around the circle, and all you're left with is pi over 4. So it's distance of 2 revolutions and pi over 4. Now, personally, I often just think it's a lot easier to just buckle down and do the loops around the circle. It's a lot more tangible to me to kind of work my way through the circle. So I totally understand if you don't want to do it this way, right? That's fine. You only need to be able to find the terminal point. If you're able to find the terminal point, I don't care how you did it. Okay. So let's do another one. I'm going to do a negative one. Maybe I'll make a note here of what I just said. Note. As long as you're able to find the terminal point, it doesn't matter how you got there, right? So as long as you are able to find the terminal point, it doesn't matter how you got there. So however you want to brute force it, you want to kind of get there, it doesn't matter, okay? Maybe you've got this like crazy brain that just sees the unit circle and you're able to loop around really quickly. That's great. As long as you're able to find that terminal point, it doesn't matter how you got there. That's not going to be something that we're testing. We just need these terminal points for what we're doing later. So let's do another, let's do this one that we said. So like I said, however you want to get there, I am on board. For me, right, I think that it's a lot easier to just kind of buckle down and count the loops. Sometimes I'll see, okay, 3, so then 6 pi over 3 would be one revolution, right? Here it's negative, so I'm moving clockwise. So 6 pi over 3 is one revolution, and then I can pull away 6 from 11, making 5 pi over 3 left over. But because I think the unit circle that we have is the most easiest to look at, how about we use that? And then however you get there, just be proud you got there. Okay. Okay. Because it's over 3, I'm moving in increments of pi over 3. Move in increments of pi over 3. Pi over 3 are here, right? Pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3. So it helps if you're able to kind of map out. And it would be so great if they made like unit circle sticky notes, because then you can just grab one, stick it on there. They don't, but maybe they do. I don't think so, but I do think it would be really handy, because then you could just kind of grab them and go. But I'm lucky because I can just copy paste, but I'm thinking for you at home. So we're moving in increments of pi over 3. So here we ended up at 6 pi over 3. So now that I've got these all blocked off, right, 7 pi over 3, 8 pi over 3, 9 pi over 3, right, 10 pi over 3, 11 pi over 3. I forgot I was moving in the negative direction. What changes? Well, from the negative direction, I know I have to go one revolution. Boop. So that's negative 6 pi over 3, 7 pi over 3, 8 pi over 3, 9 pi over 3, 10 pi over 3, 11 pi over 3, puts me at the same terminal point as pi over 3. Right. So therefore, negative 11 pi over 3 and pi over 3 are coterminal. And then later, what we need to extract out of this is, okay, if I give you an angle of pi over 3 later, x is 1/2, y is root 3 over 2. Good. So for my last couple of minutes here, I do want to talk about how these distances are actually angles, not angles in 360 degrees in a circle, although definitely that's going to become handy. But we're going to talk about radians. Now, the radians, and I know I'm cutting it close here, but 6.1 is called the angle measure. And all it's really doing is it's making that link between the distance, and maybe I should include the distance and the distance around the circle and the angle. So if a circle of radius 1, so if we have a unit circle, is drawn with the vertex of an angle at its center, okay, so the vertex of the angle is just the kind of the angle, I guess. Then the measure of this angle in radians, which we abbreviate rad, is the length of the arc that subtends the angle. Subtends meaning just takes you from the standard position up to that point. So here, just some common radians. So notice, right, that these angles, which we usually have little kind of angle measures here. Oh, this is a right angle. What's kind of mind-boggling about radians is that the distance along the circle, the unit circle, is also going to be the angle in radians, and that's where I'll write that down. But the distance along the unit circle will be the angle in radians. We said that, okay, halfway around the circle, full way around the circle is 2 pi radians. Now we have an angle. If I go from standard position over to the negative x-axis, then I've moved pi radians. So we'll keep talking about radians next day, but have a look at that handout and you'll see the connection, because we're more used to talking about degrees, but we're going to be moving to radians. All right. If you have any questions, let me know. Otherwise, we did it. Some trig here. And I'll see you on Thursday.